In this video, we are going to look at coordination compounds and ligands. Particularly, this video is made for ligands. We are going to look at ligands, various types of ligands. What are ligands? We can also say ligands. So that is what we'll be doing for this. We'll be doing in this video. And assuming if we have we can have a metal surrounded by H2O, or we can have a compound in this form, H2O. So we can represent this in a curly bracket, Mg into bracket. How many number of H2O do we have surrounding the metal atom or the metal ion? We have 4. So H2O. So 4. So you see, this is a coordination compound. For example, this is just for illustration's sake. And we can also have another atom outside this box. For instance, let's say chlorine. So anything outside the box can be represented here outside the box. So now this for now we have something called coordination sphere. The coordination sphere is a metal atom with its surrounding ligands. So these are called ligands. So now let's define our ligand. Our ligand is any atom or ion directly bonded to a metal atom in a coordination complex. Is that okay? A ligand, any atom or ion directly bonded to the metal atom. This bond is formed by the ligand usually has a pair of electrons that it can donate. It can donate completely to form a bond with the metal atom. And this bond is coordinate covalent bond. It is a coordinate covalent bond. The ligand is also a Lewis base. A Lewis base because it has a lone pair of electrons that it donates to form a bond with the metal atom. So far, I think I'm able to explain what a coordination compound is and ligand, what a ligand is, and then counter ion. So anything outside the coordination sphere becomes a counter ion. It can be here or here, so it is called counter ion. As far as it is outside the square bracket, it becomes a counter ion. So now, let's look at the ligands into detail. Let me change the sheet. Let's look at ligands into details. We have denticity, something called denticity of a ligand. Denticity of ligand. Sorry, of a ligand. Denticity of a ligand is simply the number of donor atoms in a ligand that can be bonded to the central metal atom in coordination complex. Simple, we have a lot of ligands, like we have Cl called chloro as a ligand, H2 aqua as a ligand, NH3 amine as a ligand. I have video on various types of ligands and their names. You can check them out. So this is video 2, and it's going to tell us much about ligands. So this video is going to tell us much about ligands. So the denticity of a ligand is the number of donor atoms in a ligand that can bond to the central metal atom directly in the coordination complex. So what does this mean? When we talk about denticity, here now we can talk about monodentate ligands. Let me write this here. Take your time. You are going to understand what is meant by denticity of a ligand. I just want to illustrate it in a proper manner. So we have monodentate, and you can also get bidentate ligands. So we say denticity of a ligand is the number of donor atoms in a ligand. We have some ligands that has only one donor atom. Example, if you have one donor atom, then you are called monodentate. Examples of monodentate ligands are chloride ion, water. You are monodentate because you can only donate only one lone pair of electron at a time to form a complex with a metal atom. Chlorine, if we have this as our metal atom, let's say magnesium 2 plus, chlorine can only form only one, can use only one lone pair of electron to form a bond with the metal atom. Same as water, H2O, can only use one of its lone pair of electron to form a bond with the metal, H2O. So that is why it is called monodentate ligand, because it has only one donor atom, which is the oxygen, and it's going to bond to the metal through the oxygen. And then we also have OH as a monodentate ligand, or unidentate ligand. It's also the same. We have NH3 as a unidentate ligand. I hope I'm making sense. So for bidentate ligands, those ligands, they have two donor atoms. So examples of bidentate ligands are ethylenediamine, usually represented by EN. The short form of ethylenediamine is EM. And for me to explain how ethylenediamine is a bidentate ligand, I have to try and draw the structure of ethylenediamine. And then let me try this. So this is the structure of ethylenediamine. We have it as H2, CH2, NH2, NH2. This is the structure of ethylenediamine. You can also draw it this way. It's also accepted this way. NH2. Why is it a bidentate ligand? It is a bidentate ligand because ethylenediamine, each of these nitrogen atom can join to a metal atom. That means it has two donor atoms. Therefore, bidentate ligand. Here, monodentate ligand because there's only one donor atom. The only way this water aqua can form a bond with a metal is through the lone pair on oxygen. So oxygen alone, here chlorine alone, here oxygen alone, here nitrogen alone. So that's why they are monodentate or unidentate. So bidentate, it has two donor atoms. So nitrogen can form. If we have a metal here, for instance, magnesium here, this nitrogen can form a bond with a metal, magnesium. This nitrogen can also donate a lone pair of electron to form a bond with magnesium. So that's why it is bidentate ligands. So ethylenediamine is one of the bidentate ligands. And the second one is oxalate ion. Which is represented by C2O42 minus. The oxalate ion, let me draw the structure of oxalate ion. This is oxalate ion. So this is its structure. It is C. We have double bond oxygen here, and oxygen here with a lone pair and a negative charge. Oxygen here with a lone pair and a negative charge. So now, this oxalate ion is a bidentate ligand because each of these oxygen can donate lone pair of electron to form a bond with the metal complex. So this is why sometimes you have chelating agent. This oxygen can form a bond with the metal. At the same time, this one to also form a bond with the metal to form a full substance, like it's going to form a cover on the metal, and therefore it's also a chelating agent. Chelating agent because it's like it can engulf. It's gonna look like it engulfed the metal atom or the metal ion. So I think that is that for we are done with bidentate ligands and monodentate ligands. Let's look at the other types of ligands. We have another one called ambidentate ligands. Ambidentate ligand. So far we are okay with monodentate ligand and bidentate ligand. We have ethylenediamine and oxalate ion. So let's look at ambidentate ligand. What is an ambidentate ligand? Let me list examples of ambidentate ligands before. For ambidentate ligands, they have two different atoms to donate one pair of electron at a time. Listen to this very careful. Two different atoms that has lone pair of electron. Each of them has lone pair electron, but these different atoms can form only one bond at a time with a metal. So let's say example is SCN, in which its ligand's name is thiocyanate, and the reverse of this kind of like a NCS is isothiocyanate. Have you seen the difference? So SCN, in this case, we can have a metal complex, assuming I like using magnesium, in which thiocyanate form a bond with a metal complex like 2s, like our sulfur is a donor atom. We can also have another one in which nitrogen is the donor atom, for instance. So that means that our ACN is an ambidentate ligand because it has two donor atoms. At any point in time, sulfur can donate two lone pair of electrons to form a bond with the metal, and at any point in time too, nitrogen can also do that. But this can happen like only one of these, sulfur, either sulfur or nitrogen is able to form a bond at a time. So that means that it has two different donor atoms, but only one can donate a lone pair of electrons to form a complex with the metal. I hope I've explained this clearly. I don't know. If you have anything, you can ask in the comment section. If you have contributions, suggestions, you can let me see you in the comment section. So this is an ambidentate ligand, SCN, thiocyanate, isocyanate. You see, so thiocyanate is an ambidentate ligand. Either it is thiocyanate or isocyanate, because at any point in time, sulfur can donate electron to form a bond, or nitrogen can also do the same. So another example is NC. At a point in time, if we have the metal ion, NC can form bond with the metal through nitrogen, through carbon, and also through nitrogen. Because look at the structure of NC, N triple bond C. At this point in time, carbon has one lone pair and nitrogen also has one lone pair. So one at a time, carbon can form a bond with the metal. We can also have a situation where nitrogen will form a bond with the metal. So that is why we call this ambidentate ligand. So that is for ambidentate ligands. And then the other one we are going to look at is a polydentate ligand. Polydentate. Polydentate. Polydentate ligand. A typical example of polydentate ligand is EDTA, ethylenediamine tetraacetic acid, short EDTA. It's a polydentate ligand because it has more than two donor atoms. It has more than two donor atoms which can donate electron at a time to form a bond with the metal. So let me draw the structure of EDTA to show you something. So EDTA, the structure of EDTA is we have O double bond O CCH2. You have a nitrogen here. Right. I want to just want to show you something. So we have O CCH2 bonded to nitrogen. We have CH2 CH2 Notice where I use white pen to write the atoms. We have CH2, CO, CH2, CO, O, O. So this is a structure of EDTA. So it's a polydentate ligand. EDTA is a typical polydentate ligand because at any point in time, like EDTA, mostly it has two, like more than two donor atoms. We have nitrogen, nitrogen here, oxygen, oxygen here, oxygen, oxygen here. So the density of EDTA, density of EDTA is 6. Why 6? This oxygen can form a bond with the metal. This can also do the same. This nitrogen do the same. This nitrogen can also do the same. This oxygen can do the same. And this oxygen can also do the same. So 1, 2, 3, 4, 5, 6. That is why the density of EDTA is 6. So it has 6 donor atoms. So in this case, EDTA is also a chelating agent. A chelating agent because if we have a metal ion in a solution in the presence of EDTA, EDTA can engulf the metal ion. Like it can cover it. It will form a web with the metal ion. I don't know whether that is the right way to say. Like it's going to engulf it. So that is why EDTA is also a chelating agent. Bidentate Bidentate ligands you can also do the same. For instance, oxalate ion can also do this. Ethylenediamine can sometimes do the same because it has two donor atoms. So these two donor atoms can form a bond with the metal ion at a time. But that of EDTA is very strong. Like it's going to form a very stable complex. The EDTA is going to form a very stable complex with the metal ion. So that is why it is applicable. EDTA, the use of EDTA is applicable in medicinal and in compleximetric titration. So EDTA is used as a chelating agent in compleximetric titration because when we have a solution that contains metal ions, like we want to know the concentration of the metal ions in the solution. Let's say we have a solution that contains Mg plus, Mg2 plus ions in the solution, and we want to know its concentration. What we have to do is that we have to know a known EDTA. We have to like look for a known an EDTA with a known concentration. So we titrate the EDTA against the metal ion solution to form a complex because EDTA is a polydentate ligand, also known as a chelating agent. Is going to form a very stable complex, going to surround the metal ions, each metal ions in the solution, and form a very stable complex. And in this case, we will use a metal ion indicator. Once the EDTA form a stable complex with metal ions in the solution, then the color of the solution will change, indicating an endpoint in the titration. So now, we know the concentration of the EDTA that we use. So we use that, and using stoichiometry coefficient, we balance equations and calculate for the concentration of the metal ions in the solution. Because we know the concentration of our EDTA and the volume of EDTA that will actually give us our endpoint. And definitely we're also going to know the volume of our metal ion. So what we will be left is to look for concentration of the metal ion. So if we balance the equation, we'll be able to calculate for the concentration of the metal ion. This is why EDTA is used in compleximetric titration to determine metal ion concentration. So another way EDTA is applicable in the medicinal area, like in application in medicinal area, is in medicine. Chelating agents like EDTA are used to treat metal poisoning by binding to the toxic metal ions and preventing them from interacting with vulnerable biological components. Like I think this one is very understandable. So the EDTA are used to treat metal poisoning by binding to the toxic metal ions. If the EDTA is introduced into the system and we have toxic metal ions, the EDTA is going to form a stable complex with the metal, preventing it from, since the metal is poisonous, in EDTA form a stable complex with the metal ion, it's not going to have a huge effect on the system, I mean, on the biological component. So this is the end of this video. So thank you very much for watching, and don't forget to subscribe and like. You can also share my video to with your friends. If you found this video helpful, kindly subscribe, and don't forget to also click on the notification bell for more videos like this. Thank you very much. God bless you. Stay safe. In case of anything too, you can also let me hear you in the comment section.